Well, thank you. It's wonderful to be back in Unam. Firstly, I love large polluted cities. That's where I spend my lifetime work, but I also love cities with deep cultural history, and there's very few cities in the world that have the cultural history of Mexico City. Okay, well. So where shall I aim it? This one? Anyway, so for 50 years, I have done research in the atmospheric sciences on the mesoscale. And basically it involves observations, analysis, and simulation of polluted coastal urban atmospheres. And in the last 10 years, of course, in a changing climate. And basically there's two sides to the research: how cities and their development and how pollution create new climates in cities, and how that new climate then controls the spread of pollution within the city and downwind. And these have many applications in the studies of climate, weather, air quality, emergency response. And I've studied a large number of cities, a few studies with Iran. Today I'll be showing mainly results from Los Angeles, Beijing, New York, and Houston. They told me to aim it in the back, but aim it to the front, yes. Well, even that. Okay, I wanted to go back and point out that I have two new affiliations, part-time, and that's the Institute for Urban Meteorology in Beijing and the Noah Crest facility at the City College, where I did my undergraduate meteorology degree. And we just had an international conference there, and I was in a place where I had taken classes 50 years before. So I enjoyed saying that. And so I wanted to acknowledge that this covers many projects with many different funding sources, and I just wanted to mention Jorge Gonzalez's name. He is in charge of the program in New York, and Dr. Miao is in charge of the program at IUM, and the student I'm working with is Jingjing Do, and there are many other students and colleagues who I'll mention as we go forward. So the outline, the two big topics, I guess, the first one is climate change, and just on very quick reminders, because everybody here knows and believes in global and continental climate change. And then we'll take a look at the basics of urban climate, and we'll take a look at what it takes to do a good case study analysis of urban climate and what it takes to do a good climatological analysis. And we'll have to focus today on urban heat islands and velocity in cities, and my new love for the last 10 years, thunderstorm precipitation. There will be air quality applications as we go forward. And then we'll take a look at the interaction of global change and urban change. And I'll show you two observational studies and then 4 urban WRF, that's a model I'll describe, modeling studies. And I want to stress as I show you these, how to design these studies correctly and how to control the graphics. You can do great studies and you can press a button and Urban WRF will give you graphics that doesn't show you anything. You have to seize control, and I'll show you some illustrations. Select the colors, select the increments, select the times, select the heights, etc., or else you don't see anything. That's a value. And then we have a few minutes at the end to take a look at what the future directions are, perhaps. So just going to breeze through this. This is the slide that everybody knows. It shows the global climate change for the last 150 years, accelerating from about 1970, the observations and the models. And the models have gotten pretty damn good in getting all the twists and turns. Not every single one, but for example, from the 50s to the 70s, it was actually global cooling, and the models get that. And then the global warming took off in the 70s. But it's not just one number. All this argument, whether it's 2 degrees per 100 years, every continent is different. Every area of a continent is different. And this is some of the IPCC results for 6 different continents. And the blue trends are only with natural causes, and the red trends and the black observations are from a combination of natural and anthropogenic causes. So again, I hope I don't have to convince anybody that anthropogenic modification of the global climate, even on the regional scale, is real. Of course, sea levels are rising in the last, whatever that is, 100 years. Again, those are the 2 main impacts that I'm going to be talking about, the effect of rising temperatures and rising sea levels. Some impacts, I don't have much time to discuss that, but for example, in the lower right, there is a trend over from about 30 or 40 years of hurricanes. The total number of hurricanes stays the same pretty much, but the red line shows the Category 4, Category 5 severe hurricanes. They have risen up dramatically. So climate change doesn't seem to be producing more hurricanes, but it produces stronger hurricanes. On the top slide, it may be hard to see, it's a local slide showing the spread of malaria in the United States. As the climates warm, the insects, mosquitoes that carry malaria can live further and further north. The solid black line is where that was, and I can't really read it, but let's just say 1970. And then the dashed line and the red arrow shows the movement north over a 30-year period. So diseases are spreading towards the poles as the climates change, and the climate at higher latitude is like what the climate used to be at the low latitudes. In the lower left-hand corner, there is a graph that shows perhaps a good change, and that is the decrease in frost days, and the increase in frost-free days. So the red areas have increased in frost-free days. So higher latitude areas in the northern hemisphere are going to benefit. The crops are moving northward. Crops that are grown in the United States are moving northward and eastward, and they're moving into Canada, and the same thing is happening in Russia. People move to cities, and they continue to move to cities. The 2 lower lines in green show the developed world population in the last, it projects into the next 10 years, so it's over an 80-year period, and the solid squares are the urban population, and you can see that over 50% of the population lived in the developing world cities since about 1950. That critical point was only crossed in about 2015 in the developing world. But on the vertical axis on the left, that's the actual population, not the percentage. And the actual population in the developing world is a total of about 6 or 7 billion compared to about 1 billion in the developed world. So it doesn't really much matter what goes on in the developed world. The future of the earth depends on what goes on in the developed world. In the 50s, the developed and the developing world. In the 50s, the developed world could have made a difference. When we were putting out over 50% of the pollution just in the United States, we could have said, hey, this is a golden opportunity to make money. We can develop technology so that when China rises, it can use our technology and not make the same mistakes we made. But we didn't do that. And we could have made a fortune selling them that technology. The Chinese aren't going to give up their lifestyle so you and I can continue living our lifestyle. They want the same lifestyle. And they say, you put in this much pollution, we may be putting in more pollution per year, but when we get up to this level total, then talk to us about doing something. They want the same lifestyle. They have to use the same technology because new technology was never developed to help them. So living in cities can be dangerous. And this is a slide from Alexander Bottomup, who heads up the World Meteorological Organization program on urban hazards. And you have, of course, air pollution. You have heat waves that are made worse by urban heat islands, which we will discuss, and that produces thermal stress. We have flooding, sea level rise, storms coming into cities, and that creates public health problems, energy usage problems, water sustainability problems. Excuse me. And as the climate change, all these problems become intensified. This is a report that came out 2 years ago from the WMO, or WHO, World Health Organization. Almost 2 million children die every year due to pollution around the world, most in the developing world, most in China, actually. Not the majority, but the plurality in China. This is cities, and this is pretty old, but this is cities with more than 1 million people, and most of them are in coastal areas. And there are many cities that have more than 10 million people, but I don't have time for all my slides. So we already know that coastal areas are dangerous, but all these people, 200 million people, live in cities that are only a meter or less above sea level. And these are catastrophes that have happened along the American coastline, along the Gulf Coast, and along the Atlantic coast. Every one of those red dots is a multi-billion-dollar effect from a storm, from flooding, etc., from heat waves, mostly from flooding. And it's only going to get worse. These are estimates from UNEP, that's another UN agency. And if you look on the right-hand green graph, it shows losses projected for 2030 for a 1 meter sea level rise. Most of the losses are going to be in Asia, almost $1 trillion. The smallest, or second smallest losses will be in Latin America. People die from heat waves, which are made worse by living in cities, as we'll see. And the worst heat wave on there in 2003 in Europe killed tens of thousands of people. Excess deaths. Many more died, but many were expected to die, and these are the excess deaths from those heat waves. There's the concept of environmental injustice. This is a map of the city of Philadelphia, one of the major cities in the United States. The gray lines are zip codes. And people who live in this zip code are poor. They live to an average of 68 years. People who live in this zip code 5 miles away live to an average of 88 years. Now, not all of it is climate, but it's poverty and climate, and their poor neighborhoods are polluted neighborhoods. Poor neighborhoods are neighborhoods that suffer heat wave stress. And 1 in 6 people in the world live in unofficial cities, squatter cities. They just set up a tent, and they don't have any services, but that's the only way they can live. Okay, so that sets the stage of what's going on global change, and now we want to take a look at the science of urban climate. The cities have a different climate because lots of things go on in the city. You take grass and soil and you replace it with concrete and buildings, and you alter all the surface energy fluxes, heat, moisture, momentum. You consume fuel, and you know it produces heat and pollution, but it also produces moisture. You have buildings, and that reduces the sky view, and you have pollution layers. Both of them alter the incoming solar and outwave infrared radiative fluxes. Soil moisture can be higher or lower in the city. Normally we think of the city as dry, but if you think of a desert city like Phoenix, Arizona, where they irrigate, it's actually moister than the surrounding desert. And finally, all those things affect temperature. The last one here affects the wind speeds, and that's the buildings themselves and the increased surface roughness associated with the buildings. They lower the urban wind speeds. Now, when you look at those first 4 that affect temperature, some of them you'll see act to make the temperature higher, some of them act to make the temperature lower. So there's no one simple answer. How does a city affect climate? Before we get to the details, I just want to point out that I'm mostly interested in the urban boundary layer. But of course, I have to study what goes on near the surface also in order to get the boundary conditions to understand how the city alters the entire urban boundary layer up to 1 kilometer or 2. Okay, so as I go forward, I'll sort of make key points. These are points learned the hard way. It's very easy to say, oh, you should do this, but that's only after my students and myself did the wrong thing and had to redo it. So the first key point is that urban weather, urban climate results from battles. Because, as I showed you in the previous slide, there are conflicting processes that alter the energy, the momentum, the moisture in cities. So if you look at the resulting parameters, you'll see that some of them always change in one direction. Sometimes when I pause, I'm giving the overworked translator time to catch up, because she translated to English for me, and I saw what a wonderful job she did, but I saw how when the speakers talked a little bit quickly, she fell behind. So if you see me pausing, moving, stopping, I'm only trying to help her. So anyway, visibility is always decreased, turbulence is always increased, and we're not going to have time to talk about one of my favorites, how sea breeze fronts move over cities, but they're always slowed down. The ones we're going to concentrate on, first and foremost, temperature. And if temperatures increased in a city, you get an urban heat island, but sometime, in the case, for example, of that oasis effect in Phoenix, Arizona, you can actually get a decrease of temperature in the city, an urban cool island. Those are rarer. Mostly, we're dealing with urban heat islands. Now, the next 4 I've clumped together because they're all related. So wind speed is sometimes increased, sometimes decreased. And we'll go through the details of all this. Wind direction sometimes converges into the city, sometimes diverges around the city. Thunderstorms, my favorite, are sometimes triggered, sometimes split over the city. And precipitation is therefore sometimes increased over the city, sometimes decreased over the city. Now, of those 4, of those 8, in fact, let's say the 4 on this side with the number sign, that is due to heat island effects. The other 4 on the right-hand side of each of those pairs are due to building effects, building barrier effects. And they're in a constant battle. Well, I guess I'm a low-tech guy. Okay, so the first parameter we're going to look at is temperature. And I'm going to show you a mixture of old and new studies. The old ones are mine, the new ones are mine also. But anyway, so this is the first study to probe the urban boundary layer. Remember, I showed you that slide and I said I'm up there in the boundary layer. I was a graduate student on the very first urban air pollution project. My professor died. I inherited his mantle and his data. And so he got $5 million in the 60s. You can imagine what that is today. And we gave $1 million to a young couple, and they bought a helicopter. And they measured the urban boundary layer by helicopter. Before the Federal Aviation Administration knew what was going on, they were coming down to the ground in Central Park. They were coming down to the ground over the East River. It's not possible to do this study again in this detail. So the one on the left there is a series of helicopter soundings shown by the thin line, the vertical lines. I can't read it from here, but it goes up to about 700 meters. And the gray areas are inversions. Now, you know, if you study meteorology, outside of cities at night, you get a surface-based radiation inversion that cools as the ground loses long-wave radiation. So, north of the city, there is the surface inversion at several hundred meters deep. South of the city, here's the inversion. But over the city, there's no inversion. We get an urban boundary layer. And that is hot because, well, hot. It's warmer because of the urban heat island. It's well mixed, so it's adiabatic, so it doesn't have the static, stable stability of the inversion. And all the pollution is trapped there. You might say, well, that's bad. Well, if all that pollution was released into a surface inversion, we'd all be dead in cities. So the city creates breathing space. It creates a layer several hundred meters deep so the pollution can mix up. The concentrations are lower because it's not all trapped near the building. So anyway, this is a thermal structure at night over cities. We call it a pollution dome, a heat dome. It was my master's thesis, published in 1968. When I first went to Japan, 40 years later, they thought I was dead. They didn't know I was 27 or so when I published that. They figured I was some sort of senior professor and had died along the way. Anyway, one of the other results showed the urban heat island as a function of height. People had measured the urban heat island at the surface, but no one had ever measured the urban heat island with this kind of data. And you can see it has sort of an expected, almost linear decrease with height. The horizontal bars are standard deviation. This is the average of many, many, many nights. And you'll notice there's an interesting effect here. It's actually cooler above 300 meters. The dome here is about 300 meters deep, and that's the height for most major cities, the layer in which most major cities can affect the meteorology, the urban boundary layer. Can be deeper during the day. I've been asked to go slower. Thank you. It can be deeper during the day, up to 1 kilometer or 2, but most of the interesting effects occur at night. And for major cities, the region of impact is about 300 meters. So the first lesson you learn here, there's not just one urban heat island. The urban heat island depends on height, not only at the surface. What is the effect of these little inversions? I didn't mention it, but the inversions are only a few tens of meters thick and only a few tenths of a degree in temperature increase, but they are absolute barriers for the upward diffusion of pollution. So this is from a different day, but it's the same idea. There are two urban-induced inversions here. I'll use my own. Well, I just learned this one, but now I have another one to learn with 5 buttons and not 3. So there are 2 urban-induced inversions, one at 300 meters, the magic number over New York, and then 400 meters. All the area source emissions from all the buildings, this is sulfur dioxide, get trapped by this puny little inversion. There's no pollution here. But a power plant plume from the local power company had enough plume rise to penetrate through the first inversion, but not through the second inversion. The power company loved this. They said, oh, our pollution doesn't affect the city. They forgot about fumigation in the morning. The point is, however, that there is a third inversion, much stronger inversion. You see that in the National Weather Service radiosonde sounding. But that has nothing to do with calculating pollution in a city. If you only use that, you would say, oh, all the pollution is mixed to 1,000 meters because that's the lowest inversion. Unless you have special measurements to see these shallow urban-induced inversions, you cannot do your pollution calculations properly. So the urban influences have big effects on pollution. Probably the battery is run down on that one. So here is a classic study done right here in Mexico City by Ernesto Jorge, I'm sorry for mispronouncing his name. You probably remember him. He only passed away a few years ago, and he was in this very department here. And this is the classic urban heat island study that was able to be done without having those helicopter soundings. And it provided a lot of information to compare the heat island changes in time. Here we are in 1986 with a 2-degree heat island. Here in 26 with a 4-degree heat island, much larger area as the city grows. Yeah, so this is not the whole story, as we saw with the results from the New York study. slowly. There is an award given out by the International Association for Urban Climate. It started in 2004. The face of urban meteorology in this decade, this generation, Tim Oak, we'll see his name a number of times. He was the first winner. Ernesto was the second winner. And then came Ari Bitan from Israel, Yoshino from Scuba, and then the youngest person to have won it at the time, me, from San Jose State. I don't have the winners since then. And it's given for a lifetime achievement in research on urban climate. So Ernesto was a guiding spirit. Now we have some new technology to measure heat islands. This is a hyperspectral imager, and this is New York skyline, and this was taken across the Hudson River from New Jersey, and you can get the temperatures of all the buildings, not only the air temperature at 2 meters, but you can get the temperatures in the buildings, and you could do this every hour, every 15 minutes. You can see the change in temperature. You can get the heat storage. So you can know the division of energy, how much goes into heating the atmosphere, how much goes into heating the buildings. But this hyperspectral imager has many different wavelengths that you can measure at, and you can see carbon, I believe this is carbon monoxide being emitted into the atmosphere from these buildings, and these are chemicals released from the cooling towers that don't normally occur in the atmosphere. So this is a very powerful new tool from a colleague at New York University. And these are daytime heat islands. Daytime heat islands are much larger than nighttime heat islands, especially at the surface, not necessarily at 2 meters, but at the ground. And that the ground surface is very important for convection, for example. Okay, we'll have to go through these other parameters quickly. We're going to take a look at wind speed, and there's 2 basic scientific facts you got to remember, because they're going to keep coming up. During the day, the speeds are fast, and therefore the heat island is weak, or the heat's blown away, and the roughness of the city decelerates the flow. That's one to remember. The other one is at night, the wind speeds are slower, the heat island can pile up, is larger, at 2 meters at least, and then you have acceleration into a thermal low that forms over the city. And if you look at these results, they're taken in New York, and they're taken by balloon launches, and there were 2, an urban balloon launch and a rural balloon launch. And if you plot the difference, you'll see that up to 300 meters, a magic number. Once again, the wind speed is decelerated over the city. But just like in a sea breeze situation, the pressure surfaces are altered by the dynamics, and in the upper level, the speed is accelerated. Just like in a sea breeze, you have a return flow in the opposite direction. So if you said, well, what's the impact of the city over the urban boundary layer up to, well, I can't see, but about 600 meters, you would say the average impact is 0. But that doesn't tell you anything. You have to look at the impact at every height. So the conclusion is that, again, urban impacts depend on background wind speed, they depend on height, they depend on time, whether you're fast daytime or slow nighttime. This is fast daytime. You can see the wind speeds here are over 3 meters per second. That's the critical speed. Below that, we get the acceleration into the city, and you get a curve that's exactly flipped. The lower levels would be increases, the upper levels would be decreases. So please try to remember this, because I'm going to count on you to remember it. I'll try to refresh you, but this is a first basic important point. Third parameter is effects on wind direction. So again, we have 2 classes. During the slow synoptic periods, again, we said slow winds give large heat islands, and I mentioned you get low pressure. You get convergence into the city. This is Frankfurt, and these are measurements not made by me, showing that the wind is converging into the city because it's a large heat island. The heat island is not shown. On the other hand, in New York, we had a daytime case. We had lots of observations, and each of those dots, you can't really see them, are observations. And we then interpolated those observations to grid points and then calculated the divergence from du dx plus dv dy, my only equation. And this is a plot of that divergence field. And the units on this scale are 10 to the minus 4th per second. On the synoptic scale, 10 to the minus 5th. On the general circulation, 10 to the minus 6th. And a sea breeze front, 10 to the minus 3. But on the mesoscale, 10 to the minus 4. It depends on delta x and delta y in the denominator. Anyway, the bottom line is, here's the background synoptic flow. It hits the city. The flow diverges around the city. These are divergence values. And then it converges with the undisturbed flow as it goes around the city. This is where we're going to see the precipitation effects over the city versus on the lateral boundaries of the city. We have no observations downwind of the city, so we don't have the reconvergence, this flow as it goes around. The city is an obstacle. As it goes around, it reconverges downwind. So we got two things now to keep in track. We got to keep in mind the effect on wind speed and wind direction, daytime fast versus nighttime slow. Okay, PBL moisture, we're coming to thunderstorms. Urban vapor pressure. It decreases because there's reduced evaporation over cities, but it increases because the burning of fossil fuel produces anthropogenic moisture, mainly at winter and nighttime when we consume a lot of fuel. Dew formation is reduced in the city because the heat island means that the surfaces are warmer. So we got one thing increasing the vapor pressure, two decreasing it. Again, a conflict. Relative humidity is usually decreased because of the heat island changing the saturation vapor pressure, and that's nonlinear. It's exponential, so that predominates. Relative humidity almost always decreased. Even though the relative humidity is decreased, urban fog is increased. Why? We have lots of hygroscopic nuclei condensation. So fog forms even at lower relative humidities in cities. So moisture is a great example of all these complex interactions in the urban climate. Okay, to summarize this, how to do good analysis, whether it's case study or climatological. If you really want to know what's going on, you have to segment the data. If you average, for example, with the wind speed, you get an average of 0, even though there's a big layer of decrease and a big layer of increase. This is true for everything. So you have to segment by time, because the daytime is different than the nighttime, by wind direction, or else how do you know where downwind is? By heat island magnitude, because that's a main forcing, and we've already seen by wind speed and also by PBL height. Or else you only get these small differences between large impacts. This requires golden cases. These are well-documented cases that have a clear signal. That's what you should analyze when you're doing case studies. What you need, unfortunately, I can't give you one rule, you need experience. You need to ask the right question, and that comes with experience. The question is, how shall I segment my data? Well, you may be wrong the first time, you may have to try 2 or 3 times. The third key point is that thunderstorm precipitation is the most complex. Because you have to know the temperature, you have to know the speed, you have to know the vertical velocities, the moisture, the stability. So if you're going to use a model, your model better get all this right before you attempt to look at the thunderstorm results. And I will show you results showing that. So for the study of thunderstorms, the classic study is the Metromex study done a long time ago. And it found, and this you'll notice one thing here, it studied storms in this 90-degree arc. It turns out that was a mistake, too wide. Because what they found was downwind urban maximum. Well, it's actually not one downwind urban maximum. We'll come back to that. But even in Tim Oak, I told you the voice, the face of urban climate. For 40 years, he's been hoping to, and finally in 2018, published this book on urban climate. Anybody who wants to know about urban climate has to get this book. This photo was taken by his wife when he got the first copy, pre-copy. Shows a happy scientist. Did a lot of work. 40 years ago, he asked me to be his partner. He would do the observations, I would do the modeling. Never worked. He went through other people. 5 years ago, Jamie Voot and a few others finally got down and did it. So the main discovery from the Metromex study is the downwind urban edge. Here's the storms coming from this direction. Here's the urban areas. Here's the maximum. Well, it turns out that that's too simple. Many cases don't show a downwind urban max. For example, here we have a study done way before Metromex that shows a storm initiated over London. The city had an urban heat island and it initiated a storm. Not a downwind max. This is a new study, a radar study by Dev Niogi and a student, and we will see Niogi's name. And it shows a three-dimensional perspective. This is the city of Indianapolis, and the storm bifurcates and goes around the city. Remember, I laid the foundation by telling you in low heat island cases, the flow bifurcates and goes around the city. Well, if the flow goes around the city, then the storm is going to go around the city. So in 2011, I came up, it was an invited paper at the AMS, with a synthesis to try to explain all the previous observations, building upon all my experience. And I have two extreme cases here. In the first case, the synoptic conditions are stormy, fast winds, so you're not going to have a big heat island. You have a small heat island. Therefore, we already know, you remember, that the flow diverges around the city, like we saw in that calculation for New York. And then, therefore, the storm diverges, bifurcates around the city. Therefore, you have a minimum precipitation over the city and downwind of the city in a rain shadow, just like Niogi's stuff. And the maximum is on the lateral boundaries as the flow goes around the city. That's one case. In the other case, there's no regional storm, slow winds, no clouds, a large heat island. Well, then you get convergence into the thermal low that forms over the city. And you get upward motion, and therefore, and that's what you saw in Frankfurt, storms form over the city, and you get a maximum over the city like the London case. Neither one of these has a downwind urban max. Now, aerosols have a role, but it's a secondary role, and we'll discuss it later. So I've been going to the Institute for Urban Meteorology, as I mentioned. We had a big study, which we're still in the middle of, the SURF study, that studies thunderstorms and haze. And we had a big article last July, a year ago, in BAMS, the Bulletin of the American Meteorological Society. We also had a nice cover photograph taken with that hyperspectral sensor, which our colleague from NYU brought to IUM, and they love this picture. This is the tower, and it disappears somewhere up there. They have an instrumented tower that's 350 meters with turbulence right in the heart of the city. Anyway, I can't go through all these people. There I am. There's Jorge Gonzalez. There's Fei Chen, who's the father of Urban Wolf. Walt Dabbert, past president of the AMS, very famous urban meteorologist. Just sufficient to say we got 5 generations of turbulence people going back to Mona Nabokov. This guy in the front here studied with Mona Nabokov, his students in the audience. Her student is a professor at my department, and his student was also there. So we go back, the memory goes back to Mona Nabokov. We're a young science. Okay, so our SURF study is a climatological study in which we looked at the difference between initiation and bifurcation. We did it from a climatological point of view, but we only looked at storms coming from the southwest, not 90 degrees like they did in Metromex, but it was about 45-degree arc. So, and what we did, when this is the first time it was ever done, we first looked at the heat island. And then we, without looking at precipitation, we said, okay, these are weak heat island cases, these are strong heat island cases. And we were forced by the reviewer to pick the average heat island as the cutoff. Well, so what happens? This is the large heat island case, initiation over the city. These are percentages, like a 30% increase there. Here are the storms. In the small heat island case, they bifurcate around the city. Just like we thought they would. There's a minimum over the city. There's a minimum in the downwind rain shadow. This is 35%. This is about 20%. And in the lateral sides of the city is the maximum precipitation. There is some topography over here, so it's asymmetric over here. There are some topographic influences. There ain't no downwind urban edge. This was published in 2015. Doe is the lead author. She's the student. We put that aside. We go to a second observational study involving climate change in California. We had an hypothesis. We have 3 papers. The first describes the observations. Labassi is the student of Jorge Gonzalez in New York. Basically, we said that increased greenhouse warming in the interior will increase the pressure gradient along the coast, and the sea breeze will be sucked in more. It will come in sooner, be colder, go deeper inland, etc. The bottom line is it will cool the coast. We will have a reverse reaction to greenhouse warming. We're not saying greenhouse warming doesn't exist. It exists inland, but along our coast, the extra pressure gradient will produce cooling. Now, in fact, that was our hypothesis. Someone showed us this article in the newspaper where a science writer guessed this would be the case, had no evidence, but he thought it through just like we did. And so here's our study. We started in 1970. I've showed you that we started in 1950, but nothing was happening from 50 to 70. And we can't go through all the parameters, just look at the maximum temperature. This is the sum of the LA basin and San Francisco. Maximum temperature is steady until 70 and then rises. Well, this is minimum temperature. Minimum temperature steady, and then from 1970 rises. Greenhouse gas warming, everyone's happy. And then when you look at the maximum temperature, nothing happens for the whole period. Well, there were many, many studies, they showed this, they got all excited, look, the minimum temperature is rising, the maximum temperature is not. They had all sorts of scientific explanations, but it was all baloney. Why? Because they didn't segment the data. Here we segmented the data. These are the inland warming sites, and in the inland warming sites, the temperature is rising because of greenhouse gas warming, but in the coastal sites, it's cooling. Again, if you throw all the data into one bin, what do you find? You find zero change. But that tells you nothing. All the physics is hidden. Here we look at, and so the trends are pretty big, by the way. I don't have time for the details, but in over 35 years, it's 1.2 degrees centigrade cooling. That's for all the coastal sites. This is, I have a heavy finger, evidently. This is the spatial distribution of those sites. This is the LA basin. These are the inland mountains. These are the coastal mountains. Wherever the sea breeze can come in, it brings cooling. All these blue areas, the blue dots, are significant to the 99th percentile. But maximum cooling is not at the coast because the coast has always been cooling. The maximum cooling is inland here where the sea breeze didn't used to reach. In here in the inland areas, it's warming. Here, where the mountains block the sea breeze, it's warming also. We don't know the extent because we don't have any observations here and here. So again, if you don't segment the data, you miss all the physics. It was there right in front of their eyes. Alan Roebuck, a good friend of ours, sent me this. This is a climatological monthly summary that NOAA publishes. There's California coastal cooling. Nobody looked at that. They were all amazed at the warming. They were blinded by the warming, and they didn't notice the cooling along the coast. They thought it was noise, probably. And, in fact, it was there in the IPCC. These are the IPCC from 1970 summer temperature trends. They asked coastal cooling, 1 dot on the California coast. We had a professor who we hired, but she came and gave her audition seminar, and she's gushing over all these red dots. And I said, excuse me, what about that blue dot over San Francisco? She goes, huh? Never occurred to her to look. And that's not the only blue dots. All the places in the world that have a marine Mediterranean CSB climate have blue dots. And in fact, after our paper's been published, they've already found coastal cooling in Chile. Peru, sorry. It says Peru, it could be Peru, but I thought it was Chile. Okay, so very quickly, that study showed that it was cooling in low elevation coastal areas, warming in inland. The previous studies, and there were zillions of them, all got it wrong because they didn't consider summer versus winter. They did annual. They didn't consider day versus night. We only found this during the day. They didn't consider inland versus coastal. They got 1 value for the LA basin. They didn't consider low elevation versus high elevation. They didn't consider urban versus rural. I didn't get into that. They didn't start in 1970. They got 1 number for the last 100 years. Well, they hid all the physics. But energy use, thermal stress, ozone, all depend on what's going on with these peak temperatures. So this is another study that was done by the same group, published a year later. And here we look at the trend in energy usage from those same sites. The inland sites have an energy usage per capita trend increasing, 10% per decade. The coastal sites, just a few miles away in the same LA basin, their energy usage has been going down 7% per decade. If you're going to build power plants, you might as well know where to build them. Using that 1 number from all the other studies would say, oh, it doesn't matter where you build the power plants, but why waste them in the coastal area? They need less power. Okay, we get to modeling. There are 3 different options in WRF. The simplest one is what's called the NOAA land use. It's not really urban. It's just for every land use type, it tells you in a lookup table its albedo, its surface roughness, emissivity. It has no urban physics in it. Then there's the single layer canopy model, and it has a very complex energy budget model to predict 2-meter temperatures. But the multi-layer model of Martilli, who was my student, I was not his main advisor, but he used my model to develop his scheme, has 2 parts to it. This one over here is an urban scale energy budget. This one is a building scale. Together we call them urban WRF, and it directly impacts not only at the surface, but in the PBL, the temperature, velocity, all the moisture parameter equations, and TKE. All the prognostic equations are affected as long as there are buildings sticking up into the atmosphere. And basically, it's a porous flow parameterization, and it depends on you knowing the building density. Of course, it also uses the 1-layer model for the surface energy, but it has projected the urban impacts into the boundary layer. Now, Jorge Gonzalez in New York has developed 2 new parameterizations to put into BEAM. One is a cooling tower parameterization, the other is a drag coefficient. I don't have time to tell you what exactly they are. And I just sent an email last night to Fei Chen and to Jorge to ask them whether or not it's in the new release from WRF, and we don't, Jorge didn't know. His version has it. And the other thing you need to know is the buildings. Either you use a top-down approach, say using airborne LiDAR or satellites, and you can get the distribution of buildings, but you don't learn a lot about their 3D distributions. That occurs if you knock on the door for the city planners and ask them for information on each and every building, which they have in order for taxing and other usage. So this is a bottom-up approach, and this is much more accurate. This is what's being done in Beijing and New York. I don't know, I think maybe you're doing a hybrid here, but this is the wave of the future. So here's the first study. It is basically modeling that climate change that we saw in the LA Basin. Here's the LA Basin. We, unfortunately, at the time only did 4 kilometers. And here are the results. Forget about everything except the colors. You can't really see the coastline. Both the water and the inland areas are warming. Inland areas warming more. This is at 4 p.m. and this is the area that's cooling. It matches, I'll say exactly, it's not exactly, but it matches in magnitude, timing, and location, extent the coastal cooling that we saw in the observations. Okay, that second one is a heat island study. My student, Rochelle Balmorte, and Haida Taha, whose name will pop up. Here we did 5 nested domains down to 1 kilometer. And we're using urbanized MM5. It was before urbanized WRF, but Haida, well, it was the first time that urbanized MM5 was actually run in North America. Someone brought it to EPA and left, and EPA didn't know how to run it. We volunteered and we ran it. And these are the results on 4 successive days. The city of Houston is over here. This is water over here. On 3 of those days, the flow is onshore and the city is cool. On one day, a thermal low formed offshore and the flow was along the shore and the city got hot and there was an ozone episode. No one ever captured that thermal low. Everybody had onshore flow on all 4 days. We got the thermal low because we didn't use the sea surface temperatures from the synoptic model. We used satellite sea surface temperatures. So you can spend all the time you want getting the land temperatures right. If you have crummy sea surface temperatures right, you will not get the gradient right and you can't get the winds right. And if you don't get the winds right, you can't get anything else right. I just want to show you quickly that the heat island from the Martilli scheme is much more detailed and it's bigger. It's 3.5 degrees. This is a 1 kilometer grid from the 1 kilometer grid, but without the Martilli scheme, the heat island's only half the value and not anywhere as detailed. Once we get that right, the Forest Service told us this is the tree cover with a minimum over the city, and they want to plant trees. We did not say arbitrarily, we'll plant trees. They said, we want to plant trees here, mostly over the city. So then we made a series of simulations with the trees. What do the trees do? They block the sun and they lower the heat island. And so you can see that in the area over Houston, it's cooler, but the boundaries of Houston are growing and they're knocking down trees. So outside of that, it's actually warmer. So this is a real world application of a model that works to a planning process for future. And here's the details very quickly. At 12 o'clock, and this is the run that had the maximum impact, we knocked off 9/10 of a degree from the heat island. Originally it was 2 degrees, then we urbanized it to 3.5, and then we added in the trees and we knocked off 9/10. You might say, well, who cares, 9/10 of a degree. Well, this information is used by Haida Taha in studies of the effect of the reduced heat island on ozone. Now, this is a different city, but it's the same theory. This is the high ozone in 3 locations downwind of Sacramento. They far exceed the standard, 120 parts per billion. But when you plant trees, well, here we actually whitened the roofs, increased the albedo. That lowered the heat island, and that knocked 20 parts per billion off the projected daytime max ozone. Why is that important? Because EPA, because you don't have to spend millions of dollars to reduce the emissions to lower the ozone. You can lower the ozone just by lowering the heat island. And EPA gives you 5% credit in reducing your emissions. So instead of having to reduce $100 billion, you may only have to reduce $90 billion. Well, that's $10 billion savings. So this is big money, and Haida Taha is the one who showed EPA that this is possible. Last study, the bifurcating thunderstorms that I showed you the climatological average for. We did a golden case simulation for a storm bifurcating over Beijing. It's in review for Monthly Weather Review, and we did it on a 3-kilometer grid. So here's the observations from a network of surface sites done every 15 minutes. People publish every hour. What good is it? The storm only lasts an hour. And you can see very clearly, this is the center of Beijing, the red ring road. You can see very clearly that the precipitation bifurcates around the city. This is observations, and this is the total accumulated precipitation, and you can see bifurcation around the city. This is the climatological study in which the storms came from the southwest, and this is this one case study where the storm comes from the northwest, but the pattern is just the same. A minimum over the city, a minimum in the downwind rain shadow, but reversed. This is the simulation with the city, without Beijing, and this is the difference of the total accumulated precipitation. This simulated precipitation pattern looks exactly like the previous one. Without the city, you don't get bifurcation. When you look at the difference, you see a big bifurcation. It's clearer. The only difference between this and the previous slide is that, the previous slide has a wider bifurcation angle because we underestimated the building height. We didn't have the bottom-up building data for this simulation. Well, this is the last study. It's only 2 slides. This is a study done by Jorge Gonzalez's group for the mayor of New York. The point is that the scientists must have the ear of the politicians, and Jorge has established himself. He's the chair of the mayor's mayor's panel on climate change in New York, and they give reports, and this is their last report. One of the students did a dynamic downscaling of 2 IPCC scenarios and predicted the climate during heat waves for New York City out to 2080. And the red one is the worst scenario, the blue one is the optimistic, which we'll never get to. But you can see that the mean maximum temperature goes up a lot under the worst emissions. And when you put in relative humidity and get the heat stress temperature, it goes up to over 100 degrees. The frequency seems to level off, but that's only because the durations become almost a month long. I mean, you can't have many month-long heat waves, so I told the student to plot the number of days above 90 and the number of days above 100. And you can see the disaster for the number of days above 90 and the number of days above 100 under the worst emission scenarios. Another real-world application that has the ear of the mayor of New York City. So now we have some overall conclusions. Urban climate is complex. And if you're going to study it, you have to be sophisticated in how you do it, whether or not you're doing a case study or climatological analysis. If you're going to model, best to model a golden case using highly urbanized models and good building data sets. The golden case is one that has a clear signal and lots of observations, hopefully PBL observations. In terms of climate change, urban areas both contribute to and are impacted by greenhouse gas warming. And if you want to analyze these interactions, you have to have sophisticated analysis and modeling techniques. Urbanized models can be applied for weather forecasting. I really didn't show you that. Air quality, climate and climate change, and emergency response from natural and man-made disasters. For example, 9/11. I didn't have time to get into any of those. I think this is absolutely the last technical slide. Future needs for mesoscale MET modeling applied to urban areas. Well, it's a motherhood statement. You need better PBL MET data. You need a methodology that doesn't exist and how to assimilate data on the urban scale. Satellite data, profile data. We need good schemes. I don't have time to go into the details. Better building data. We need to study aerosols. If you want to really study precipitation and radiation in an urban area, you have to have better aerosol, 4D aerosols that are not available only in WRF-Chem, and WRF-Chem is not urbanized yet. And you need to link to CFD models. We're starting to do that with a model called NVMet to study a downtown small area of San Jose. So my next proposal is to study the 4D aerosol impacts on urban bifurcating thunderstorms using an urbanized WRF-Chem with updates to the turbulence schemes both in WRF and WRF-Chem, working with Professor Zilimtikovic, if you recognize his name, and Alberto Martilli. And if I get it funded, I will need a postdoc and a grad student. Classic textbooks, some of my references, and that's it. Phew. I actually finished on the time they said I had. I think I'm close to passing out from dehydration, however.
Abrimos el foro para preguntas que tengan, por favor. ¿A quién empieza? Bueno, mientras se animan, tengo una pregunta para Bob, while students are settled down and want to ask a question. Bob, you mentioned that you planted trees in Houston.
Can I have a chair?
Please.
That's fine, that's fine. Thank you. One
of the concerns that we have here in Mexico about trees is, and a concern that we have in our department is exactly the emission of biogenic emissions. So what did you what did you do in that case study?
We're aware that trees have biogenic precursor emissions, and we work with the Forest Service, so they recommended trees that did not have those emissions. And Hyder Taha actually did the photochemistry using our output, although I didn't show it. And also we wanted trees that provided shade. So we were very specific about what would be good trees, and the Forest Service, looking over the land use, decided where is the best place to plant them. So we were aware of that.
Arturo.
Thank you for the very nice presentation, Bob. I was wondering if you could go over rather quickly over the physical mechanisms that will inhibit precipitation right at the center of the city.
Great question. I know your interest in that. And I was here one or two nights, and it was the middle of the night, maybe it was Saturday night or Sunday night, and there was a fantastic thunderstorm with lightning, et cetera, et cetera. And I looked at my watch, and it was 6 p.m., and I said That's due to downslope flow from the sides of the mountains converging in the center of the city, producing upward motion and triggering thunderstorms. So the next day I asked a few colleagues here, is this common? And they said yes. And I said, well, I think the mechanism must be this convergence, and the convergence is probably augmented by the urban heat island in the center of the valley. So I thought this would be a great study in which you could try to simulate one of these classic thunderstorms, then take out the city and see the effect of the thunderstorm, etc., and go back to when there was a lake. Ron has published papers in which, Ernesto published papers about heat islands in Mexico when the lake was still here. So you could have a whole series of 4 simulations. You get the first storm correct. You never do parametric studies until you get the reality correct. Then you know what's true. Then you do parametric studies. And the first one would be to take out the city to see its role in this convergence. The second one would be to go back to what the city was when the lake was still here. And then the fourth one would be project the development of Mexico City out into 50 years and see what the new heat island would have on these thunderstorms. But to me, knowing something about the downslope flow, I think that these nighttime thunderstorms around 6 o'clock are augmented by the city and due to the convergence in the center of the valley. So I think it's a wonderful PhD, or maybe 2, dissertation.
Thank you.
There's a question by internet, and is asking if there is some relationship between cooling in coastal areas, especially in places with more fog, with the upwelling of seawater.
Very good question also. We had superficial seawater temperature in our models. Again, they weren't satellite derived, they were from the large scale model. And in the analysis I showed, we lumped together what was going on in San Francisco and Los Angeles. Well, in fact, we found that the trend in sea surface temperature was different in San Francisco than it was in Los Angeles, 400 miles to the south. And therefore, our results have been refined by one of Jorge Gonzalez's students. So the bottom line is anything that increases the temperature and pressure gradient between the coast and inland will increase the coastal cooling, and we did not focus enough on the sea surface temperatures. So that study has to be done again, this time focusing on sea surface temperatures. And we really did not focus on what aspect of the increased sea breeze was the dominant mechanism. Was it coming in sooner? Was it staying later? Was it going further inland? We know it's going further inland. Was the air colder because of the sea surface temperature trends? So there's still a lot of work to be done in that area, focusing around sea surface temperatures.
Thanks. And there is another. So some person is asking about the urban or geographic characteristics affecting the precipitation around or in a city.
Aerosols?
Precipitation rain.
Yeah, how aerosols affect precipitation. When you run WRF, you can only specify a background aerosol concentration that doesn't change in time, doesn't change in space, unless I'm wrong, maybe they've changed it. And so we have not really focused on aerosols. But in New York, and I didn't show these results, one of Dr. Gonzalez's students ran RAMS. And he worked with the RAMS people to put in more sophisticated four-dimensional aerosols. And he showed what Danny Rosenfeld and others have found, that having lots of aerosols, like in a polluted city, will suppress the precipitation in the near field because there's too many aerosols competing for the same amount of water, but the droplets will grow bigger, and downfield, the precipitation will be increased. And that's exactly what they found in New York. So aerosols do have an effect on precipitation. Now, for thunderstorm initiation, I don't think aerosols play a big role. For bifurcation, I don't think aerosols play a big role. And I have had many discussions with Danny Rosenfeld, who's a good friend of mine, and he has finally admitted, maybe I hit him over the head once too often, but he has finally admitted that he thinks that the effects are secondary. The two mechanisms that I focus on, initiation and bifurcation, are driven by dynamics, driven by the temperature field, driven by the wind field. But once the storm is evolving, certainly the aerosols will play a role in determining the exact location, the exact amount, and the exact timing of the precipitation. So that's, again, I told you that was the actual proposal I'm writing, the role of four-dimensional aerosols on that aspect of bifurcating thunderstorms. Because those results I showed, that's the first time anyone has ever successfully simulated a bifurcating thunderstorm. And I have to admit that I'm not a thunderstorm person, and I tried to explain why. And the editor and the reviewers of Monthly Weather Review weren't convinced. And we're in revision yet again, and we focused down, and I'm trying to use the terminology and the physical understanding that they recognize as scientific. And that was the origin of my questions to yesterday's speaker, because I'm learning about vorticity stretching and tilting vorticity. And we didn't explain the bifurcation process well enough for the editor. And we certainly have not considered the aerosols yet. So this is just the first study in a long series of PhDs on bifurcating thunderstorms over cities and the role of aerosols.
Thank you for the presentation. I would like to ask, taking account this contribution of the aerosols in the polluted cities, nowadays, I don't know how the project is currently, but I saw that the mankind is able to produce artificial clouds, but I don't know how that could help us to the big cities to reduce the pollution levels. That could be a good way to solve this problem, or is that just an imaginary way to solve it?
The dean of cloud seeding for rain is Danny Rosenfeld. And in fact, he also received an award from the mayor of Beijing for his many years of work, but he also received the Great Wall Award, I think it's called, from the president of China for his cloud seeding work. Okay, now, in Israel, the only study in the world that still claims to prove that cloud seeding works is Danny Rosenfeld's study in Israel. However, two professors from his own department, I can't think of their names for the moment, they showed that even that study is not a double-blind, statistically valid study. So there is no study in the world that can scientifically pass rigor and say we produce rain. However, why do people still pay for it? Well, let's say you're a farmer in the middle of the United States and you're in a drought, and you beg the governor to pay Danny Rosenfeld or someone else to cloud seed, and you don't, and it doesn't rain, you're upset. So if you pay Danny Rosenfeld, whether it rains or not, at least you tried. And chances are it'll rain, and you can claim that Danny Rosenfeld did it. But there's no double-blind experiment that ever passed statistical test. But Danny comes the closest, and Danny still works. And here's another aspect of this. The 2022 Olympics, Winter Olympics, are outside of Beijing. And our institute, the Institute of Urban Meteorology, has to forecast precipitation and other things for those Olympics. No one in the institute has ever forecasted for the mountains outside of Beijing because no one lives there. So we are bringing in people from all the previous Olympics who made forecasts. We are bringing in scientists making measurements and planning field experiments. And they need to make snow because it doesn't snow there. They selected, they got the bid, but there's never any snow or very little snow. So almost all the snow will be man-made by snow machines, and if they're lucky, if Danny Rosenfeld is good, they will produce Danny Rosenfeld snow.
Thank you very much.
One more from...
Another person is asking about the influence of lakes in urban climate, for example, in the Great Lakes area of North America.
Influence of what?
Lakes.
Lakes. Yes. Well, you'll notice when I read out what my 50-year interest was, I left out the word coastal, large coastal urban areas. Well, because you're not a coastal city, so I figured, well, why stress that? But I grew up in New York. I live in California. Most of the cities that I've studied are on water. And mesoscale meteorology, urban and otherwise, has always studied lake effects on sea breeze fronts, lake breeze fronts, and those who were in cities on lakes always studied the urban interaction on lake breezes. And in fact, there's a lot of good research being done in Chicago now. They have very sophisticated models, and they're watching the lake breeze from Lake Michigan come over Chicago. So lakes affect sea breezes. Lakes are sources of cool air, so they mitigate urban heat islands, just like parks do. And so the work here in Mexico City by Ernesto and perhaps Aaron have showed that the old lake in the center of Mexico City did have an impact on temperatures, heat islands, etc. So that's, again, a very interesting area of research. I must say, and I hope you're not think I'm pandering, these are the most insightful questions that I've gotten at a seminar in a long time. A lot of times the questions just aren't insightful, you know. People know very little, and so they ask very superficial questions. Every one of these questions is associated, maybe they're being asked by people who are getting their PhDs on these topics, but they are PhD level research topics. It's really nice to see the number of questions and to see the type of questions. There was someone who started to raise their hand back there and pulled their hand down. That was in the very beginning. Maybe that person has left. There's a vacant chair there. Maybe they missed their opportunity.
Yeah. She left. Okay.
No more questions?
Bob, we have you already here for 1 hour and a half, almost.
Well, I took 60 minutes to the dot, and I didn't have to drop any slides. I was prepared to drop slides.
So it's bad thing.
I want to thank the translator. She's probably passing out inside there, but I listened to her translation from Spanish to English, and I was watching the speaker, and she was really stressed, but she did a fantastic job. So we should thank her. Those of you who had to use the translations, she should come out and take a bow, really.
Okay. Thank you. Thank you very much, Bob.
Ah, there she is, yes.